In this video, we want to do an example of Newton's second law in two dimensions. I have a mass, 750 kilograms, and it is hanging from two cables. One is set 75 degrees from the horizontal, and the other is 60 degrees. What are the tensions in the cables? Well, I have a picture here. I have this mass. There are two cables hanging from different angles, which I will call theta and phi. Theta, in this case, is 75 degrees, and phi is equal to 60. I want to know what the tensions are in the cables, and I think Newton's second law is going to help me out. To use Newton's second law, I first have to identify an object. The object seems straightforward enough. I'm going to look at this mass. And now I want to find all of the forces on this object. The forces are gravity and anything that crosses this boundary surrounding the mass, because it has to come into physical contact with the object. So I have the two tension forces, each directed away from the object, and of course the force due to gravity. I called force due to gravity F sub g, the tension on the left, T1, and the tension on the right, T2. Now that I've identified my forces, I need a free body diagram. I start with a set of axes that are parallel and perpendicular to the ground. That will help me find components. The force due to gravity, it's directed downward. I have tension 1 off to the left. It is at an angle theta relative to the horizontal. Now, it may not be obvious immediately that that's the same angle theta, but if you look on the parallel line up on top, you can see that this angle is in fact this angle because the tension is directed along the line of the wire, and then from the geometry rules, the opposite angle has to be the same one. T2 then points the other direction, and it is an angle phi from the horizontal for the same reason. We need a coordinate system. I've chosen positive x to the right and positive y to be up. Sometimes it can be helpful to just put which of the directions are positive and negative x, positive and negative y. That can help solve for components later. Now I'm going to apply Newton's second law. Newton's second law is the vector sum of the forces on an object is equal to the mass of that object times that object's acceleration. So that's a vector relationship, and I've written that vector relationship here. I do it vertically. That will help me extract scalar relationships and scalar equations when I write everything in component form. So I want to find the components of these vectors. We start with T1, and to find the components, I start at the tip of the vector and draw a line to one of the axes so that it makes a right triangle. Now, with the magnitude of the vector as the hypotenuse, the lengths of the sides are then the magnitudes of the components. So, for example, the length of this blue line is the x component of the force T1. The length of the orange line is the magnitude of the y component of T1. To find the x component is the magnitude T1 cosine theta. And now I look at the direction. Is it on the negative x side or the positive x side? It's on the negative x side, so that one is negative. Now I look at the y component. Its magnitude is T1 sine theta, and it is certainly pointing on the positive y side, so it becomes positive. T2, the same approach. First of all, draw a line from the tip of the vector to an axis such that it makes a right angle. So now I have a right triangle with the hypotenuse, the magnitude of tension 2. The length of the sides then become the magnitudes of the components. And I can see the x component is on the positive x-axis, and the y component is on the positive y-axis. So the x component of T2 is T2 cosine phi, and it's positive, and the y component is T2 sine phi, also positive. Next up is gravity. It has no x component, so the x component is 0. That means the entire magnitude lies along the y-axis. From the gravitational model, the magnitude is the mass times g, the acceleration due to gravity, and if I look at my diagram, I can see that it lies along the negative y-axis. Now the vector sum of all of these is equal to the mass times the acceleration, but the thing is hanging, so it's at rest, so I know that the x and y components of the acceleration are both 0. Now I can create scalar relationships from these because the x components of the vectors must add together to give the x component of the mass times acceleration, and the sum of the y components of the vectors must lead to the y component of the acceleration times the mass. And now I can use these to create scalar relationships between things I know and things I want to find. So I've just written those out there. For the x components, negative t1 cosine theta plus t2 cosine phi is equal to 0. And on the y component side, t1 sine theta plus t2 sine phi minus mass times g is equal to 0. I have two independent equations, and it looks like I have two unknowns, t1 and t2. I know theta and phi, and I know the mass and g. So I should be able to solve. Let's take a look at the blue equation first. If I bring t1 on the other side, I get t2 cosine phi is equal to t1 cosine theta, and I can solve that for t2 by dividing both sides by cosine phi, and now I have a relationship for t2 in terms of t1. I can use that to substitute into here, and I should be able to solve for t1. Rewriting that equation, where I've substituted t2 in for t2 in the orange equation, I can now do some algebra. Sine phi divided by cosine phi gives us tangent phi, and then I factor to t1 out of both terms. And now if I divide both sides by this thing, I should be able to solve for t1. So that's what I've done, and I know everything on the right, so I can plug in numbers, and I get t1 is equal to 5,200 newtons. Well, does this make sense? The magnitude seems about right. We know that the force due to gravity is equal to mg at 750 kilograms, so that's going to be something like 7,500 newtons. And I have two cables that support it, but it's not going to be exactly half because they're at an angle. So something greater than half, maybe that makes sense. What about the limiting cases on the angles? What happens if you take both theta and phi and take them to 0? What happens? Well, sine theta goes to 0 and tangent theta goes to 0, so t1 blows up. It goes to infinity. And that sort of makes sense because at theta is equal to 0, both tensions are horizontal, and it's not going to be able to support the object vertically. What about theta is equal to 90 and phi is equal to 90? I have to be careful about taking the limit as theta and phi go to 90 degrees. Because of this ratio, both cosines are going to 0. However, what happens at theta and phi equals 90 degrees is that there are no x components. You only have the orange equation. Sine theta and sine phi are both 1, and so you have tension 1 is equal to tension 2, and the sum of them is equal to m times g. That makes sense because both tensions are strictly vertical. We have tension 1. Let's go ahead and solve for tension 2. By plugging tension 1 into here, I know the angles, so I can put that in my calculator, and I get T2 is equal to 2,690 newtons.